This problem describes a solid of revolution created by rotating the given region about the y-axis, and we are asked to find the volume of this solid. We begin with a sketch of the region in 2D. For this, we need a y-axis and an x-axis. The curve e to the x squared is an even faster growing curve than e to the x, and since x is being squared, it is symmetric around the y-axis. The lines x equal to 0 and x equal to 2 are vertical lines, one of them being our familiar y-axis, and the other one, say, right here. The last curve, y equals to 0, is our familiar x-axis. Now that we have sketched all four curves, we see the enclosed region and shade it, and also indicate the axis of rotation. Let's explore this region. If we would use the disk or washer method, then we see we have to divide this region into two. In the bottom region, we would get a disk that always has 2 as a radius, while in the top region, we will get a washer, something like this. In any event, we would need two integrals. We can also employ the shell method. For this, we think of a cylinder being wrapped around the y-axis. So here is our height of the cylinder. Here would be our radius. And the cylinder would look something like this. Using the shell method, the volume is calculated as the integral from, say, A to B of the area of the shell's mantle and integrated with respect to the appropriate variable. The area of the shell's mantle is the height multiplied by the circumference. The circumference is 2 pi times r, and we've already indicated that our r is in the x direction, and our height is precisely y. Since our heights are cutting the x-axis, we know that we must differentiate with respect to x. And our heights run over the interval from 0 to 2. So these give us the integration bounds. Now we have all the information to find this volume, which is the integral from 0 to 2 of y times 2 pi x dx. We now need an expression for this height y in terms of x, and that is our curve e to the x squared. Analyzing the integrand, we observe that we need the substitution technique, and we let w be equal to x squared. Then dw is equal to 2x dx. And w at 0 would then be equal to 0 squared, which is still 0. And w at 2 is equal to 2 squared, which is 4. So our volume becomes the integral from 0 to 4 of pi times e to the w dw. Now we can readily find an antiderivative for e to the w, which is e to the w, and we evaluate this from 0 to 4. So this is equal to pi times e to the 4 minus e to the 0. And the only thing that we can simplify is that e to the 0 is equal to 1. And so this is our volume in cubic units.